Okay, so we're going to cover 3.4, which has to do with inverse functions. So I want to give you a quick, brief overview of what we're going to be doing, or some terminology and stuff. We've dealt with inverse things in the past, and you already know, for example, many inverses, like the inverse of addition and subtraction. The inverse operation of like multiplication is division. And we've learned recently about the inverse operations of things like x squared would be like a square root, and like a cube and a cube root. Okay, so there are many inverses. Well, we're going to be talking today about inverse functions. And so there are many little characteristics that functions and their inverses have. And so we're going to learn about some of these characteristics. One thing I do want to talk about is notation a little bit. Like, we'll talk about a regular function f of x. The way we denote an inverse function is to put like a -1 right here, like that. And this can be a little bit confusing, this notation, because it's not an exponent in this case. And so this does not equal, for example, 1 over f of x. That would be false, okay? So just be aware that this is not an exponent. It's just simply the notation we use for the inverse function of f. And we were learning about composite functions just in the previous section, section 3.3, where we put f inside of f, we put g of x. And a very interesting thing happens when you put an inverse function inside of a function. And likewise, if you put the function inside of its inverse. If you think about these inverse operations, they kind of cancel each other out, right? I mean, if you have x squared here and you have its inverse here, what happens? They cancel each other out, and so you're left with x. And that happens with all inverses. If you put an inverse inside of its function, it will cancel itself out, basically, in a sense, and leave you with x. So those are some of the things we're going to see here, and we're going to see other little characteristics that are quite amusing. And so this whole lesson it's a fairly difficult topic, so don't be too hard on yourself if you're finding it a little difficult to understand in the beginning. It's going to take some practice, and you might have to re-watch this more than once to get it figured out. Anyhow, be patient. It's not the easiest thing in the world. So let's get going on the PowerPoint. I'll try to cover this over a 2-day period. We'll do as much as we can today, and then we'll stop and get a second part later. So we start out by talking about inverse relations in a sense. Inverse relations are different from functions in the sense that a relation just has to do with ordered pairs. Like there's an x and y coordinate, and so there's x and y coordinates. And a function is usually some rule instead. Like, for example, we would write a function, maybe f of x is equal to, say, 3x minus 1. Okay? A relation, on the other hand, that's what we're talking about here. It just has xy coordinates. So you'll notice all these points are here. There's these blue points, like 0, 6, that's this point. And 1, 4 is this one, and 2, 2 is this blue point. Okay, so, well, to find an inverse of a relation or a function, there's a real simple trick. All we need to do is switch the x and y coordinates. And so this 6 comes up here, the 0 comes down here. And so the inverse relation would be this. And so all you do is switch the x and y coordinates. And because of that, there's a real interesting fact about functions and their inverses. There's always a line of reflection about y equals x. That's this line right here. The line y equals x is this line right here. And what that means by the line of reflection is that the function and its inverse are equidistant from the line of symmetry. Like, for example, this point here, this blue point, is referring to the 4, 1, right? Well, this distance looks like it's like two diagonal boxes. I mean, if you go down the diagonal of the boxes, well, it's maybe one and a half diagonals. Like, there's a one diagonal there and a half diagonal. So it's about one and a half diagonals of the box. Well, if you look here, there's another one and a half. There's one diagonal there and a half to its inverse. So these two distances are going to be the same. Okay? Now let's look at this one. This one's 4 diagonals. 1 diagonal, 2 diagonal, 3 diagonals. 3 diagonals, right? The inverse is also going to be 3 diagonals from this line of symmetry. So it's 1, 2, 3. So that's kind of an amusing little fact that we're going to see over and over and over again. You know, so these two segments are equidistant from line of symmetry. It's just like when we had parabolas. Remember when we had parabolas? We sometimes had an axis of symmetry. Way back in chapter 1, we might have had an axis of symmetry, and there might have been some vertex point, and we did a graph like this, right? And there's all these points that are equidistant, you know. Well, that's because the axis of symmetry is like a line of symmetry. And you can also think of it as a line of reflection. You can reflect this point over to there. Well, that's one of the little facts you're going to want to remember, is that inverses always have a line of reflection about the line y equals x. The second little fact you want to remember is that to find an inverse, usually the trick is just to switch x and y. And so we're going to do some examples where we do that. So let me get back here and move on. Oh, let's start the dump. Okay. So inverse function, switch x and y. There you have it. If you're doing a relation, it just involves points only. And if you're doing a function, it involves like some equation. So there you have it. How about that? Okay. Find the inverse. So the typical trick to find an inverse, you just switch the x and y. So you're going to write x here and write y here. And then you just solve for y. So what we would do is we would add 5 here, and we'd add 5 here. Okay, and so then we have 3y is equal to x plus 5. Now I kind of like to have my y on the left side. So I think what I'll do is just rewrite this. I'm just going to continue over here and write the 3y over here is equal to x plus 5. I don't know. For me, it just looks kind of weird to me if the y is not on the left side. Well, anyhow, we're trying to solve for y, and so I'm going to divide by 3 here and divide by 3 here. So these 3's cancel. And so I have y is equal to x plus 5. Now, this idea of switching the variables is the way that we find the inverse. What we do is this isn't really what y is. Y is actually equal to this. That's what y is. Okay, so this here is not really y. What I want to get at is this. The way we find the inverse is to switch the variables and then solve for y. And then we call this the inverse function. So we're going to take this part out and call it the inverse. Well, let me erase a little bit, make it a little bit better. So we take that out, and after we've solved for y, we then call it the inverse function. Remember, there's a minus 1 there. And so this is the inverse function of this one. Now think about this for a second. This says the original function, this is what we would call normally f of x. It's equal to y. In this case, we take some number x and we multiply it by 3 and then we subtract 5. The inverse function says, hey, we're going to take x and add 5 and then divide by 3. So it should not surprise you if there's multiplication in here, there's probably division in the inverse. If there's subtraction here in the function, the inverse is going to probably have addition. And we will see this later on, that if I were to put the inverse inside the function and I did this, we're going to see this. The thing that we get is x. It's just like I showed you before. The inverse function of a square is the square root. So these two cancel. And so you're left with x. Well, like I said, the same thing is going to happen up here. And we'll be verifying that later on. It's one of our tests. Sometimes we were given a couple functions, f of x and g of x, and we're asked to determine whether they're inverse functions or not. Well, this is what we'll do. We'll put one inside the other and see if we get x. It turns out that that only happens if they are inverse functions. So that's a real clever way to do a test, to find out if you have inverse functions or not. Interesting stuff. So anyhow, let's continue and let's see what happens here. So we solve for y. Now, I want to point out something here. When I was solving for y, divided by 3 here and divided by 3 here, that's an alternate way to write this as well. When you have x plus 5 over 3, you can separate this into two separate fractions. So you can write this as x over 3 plus 5 over 3. Either way is fine. It's just a matter of preference. So don't be surprised sometimes if you look in the back of the book and your answer is slightly different. Doesn't mean it's wrong. These are just properties of fractions. Like if you add 1/4 plus 7/4, if you have the same denominator, you can add these and you get 1 plus 7 over 4. And then most people would write that as 8 over 4 and then simplify that even further and get 2. But the point is, if you have a common denominator here, you can add them and write it as a single fraction. Okay, hopefully that hasn't confused anybody too much yet. So let's continue. Here's another problem. I'll just go through this real quick. The way you find the inverse, and you just switch variables. And so we put an x here is equal to 4y plus 2. And then the method that we find the inverse is by finding y. We just solve for y. And then whatever we get after we solve for y, that thing on the other side of the equal sign is the inverse. And so then we just replace the y with the inverse. Well, so anyhow, this is how this would work. We would just solve for y. So I'm going to subtract 2 here. Subtract 2 there. And we have 4y is equal to x minus 2. And finally, we divide by 4 here, divide by 4 here. And we get y is equal to x minus 2 over 4. Or if you prefer to write this in fraction form, x over 4 minus 2 over 4. And of course, we would simplify that. That's awkward. If fractions can be reduced, you want to go ahead and reduce them. So we could write this as, another way you could write this though is 1/4 x. You can put the x like on the side here if you want. And then minus 1/2 here. Anyhow, we no longer call this y, we call it the inverse function. So f to the minus 1 x. Again, this is not a negative exponent. It's the notation that we use for the inverse function. And there you have it. There's the inverse. Now, one of the things we will have to talk about is domain again. That's going to be coming up. Anytime you have an f of, of g of x, you have to consider the domain of the function that you're putting inside. And that's what we saw on lesson 3.3? Well, the same is going to be true when we're dealing with inverse functions. So let me just continue a little bit more, and I'm almost ready to stop. So these are a couple little facts right here. If you have a function and you put the inverse inside of there, you get x. Now, instead of writing it this way, the g of x in this case will be the inverse. So you would have f of f inverse of x is equal to x. Okay? Whoops. And likewise, you would have, in this case, you have the inverse, and you put the function inside of its inverse, and that's equal to x. So there's two ways you can think of this. In my square root of x squared, you can think of the function on the inside as the inverse of the square root, and so they cancel each other. But you can also think of it this way as the square root, and you can square x, and so the square cancels the square root this way also, and you get x. So that's a little picture of what these two rules are saying. This little picture right here. And I've gone on about 15 minutes now, so this is probably a good stopping point for part 1.